So I expect that this will communicate to you that you should get negative 10,000. And it goes back to that video that we watched about PEMDAS, about the order of operations. Right? We watched that? Okay, that guy's handwriting really fast. It could make sense that you would get 10,000, except for it would violate the agreement that we made. Okay? There's a certain shorthand that, as mathematicians, we want to be able to use, take advantage of, so that we don't have to write tons and tons of parentheses all over the place. Okay? So, if you got positive 10,000, it's probably because you did this. Negative 10, and negative 10, and negative 10, and negative 10. And if all you knew about this problem was exponents and what they're supposed to do, that would kind of make sense. Here's a number. It looks like the number negative 10. Looks like we're raising it to the fourth, which means we have 4 factors of that. We multiply together. Okay? But because of that shorthand, because we want to use that shorthand, this means if we're using that shorthand, that PEMDAS shorthand, then this is exponent, and this is actually multiplication by negative 1. So exponent comes first, multiplication by negative 1 would come after that, and that PEMDAS. So what we have is 10 times 10 times 10 times 10, and then multiply the result by negative 1, and so you get negative 10,000. Okay. And it's not mathematically wrong to multiply 4 negative 10s together, but according to the agreement, like I keep saying, the agreement that we've made, it would be wrong. Okay? So if I do write that, I do expect you to get negative 10,000, or if we put negative x to the fourth, which is more often what we'll see, something with variables in it, I want you to know that that means this number raised to the fourth power, and then a negative multiplied by the result. If I want the negative to be included, then what do I need to use? Parentheses. I need to specifically tell you that I want the number negative 10 to be written 4 times and multiplied together. Okay. All right. So we have an expression. Here is an example of an algebraic expression. It's an expression, a mathematical expression that uses addition, multiplication, subtraction, division, numbers, and variables. What algebra is could be defined as using numbers to represent, or using letters to represent numbers. You can put it that simply. That's what algebra is. Okay. So when we throw variables in there, what we call variables, we are into algebra, and it's an algebraic expression. Just hopefully what I would hope is review. If we take 5j minus 3j times 5, what are these things called? Not called base. The base would be something like the base of the exponent. Numbers. Well, they are numbers. They're special. They are the numbers that are multiplied by the variables. Okay, you get a special word for those. It starts with a C.
Coefficient.
No. It's
coefficient.
Coefficient. I'll say coefficients. Those are coefficients. If you have a number multiplied by a variable, the constant that's multiplied by the variable is called the coefficient. And what are these called? Variables. Variables. And this guy all by himself is what? Does it change? Does it vary? Constant. It remains constant. It's always 5. So coefficients, numbers multiplied by variables. Variables, letters representing numbers. And constants, numbers. Numbers that aren't multiplied by variables, they just stay what they are always. Okay. So what does it mean to evaluate that expression?
Figure out what J is. Wait, no, that's a lie.
That would, if we were to first of all, we can't figure out what j is supposed to be, right?
Okay.
What would we need in order to say j's got to be this?
Equals.
An equals. We got to have an equation, okay? So that's what that would be. But if you look at it too quick, you might see this equals and get confused. So that's solving for j. What's evaluating?
Putting it in the equation.
Put it into the expression, okay? Making a distinction between expression and equation means I'm kind of a math geek. I'm fine with that. But it is a correct distinction. There's an expression and there's an equation. Equation simply requires an equal sign. Expression looks like an equation, it just doesn't have an equal sign. It has some variables and stuff added and stuff multiplied. And without an equal sign, it's just an expression. So if we evaluate the expression, we just plug in 10 for j, 5 times 10, minus 3 times 10, times 5. And I think I still have this up. Yeah. So that I don't have to put bunches of parentheses around everything like you showed in that video. We have the order of operation. The order of operation is the thing that just saves us from writing all those parentheses down. And it's not right and other things wrong, but it's just we've all agreed. Here's what we'll do. We won't do 10 minus 3 first, because we're just going to agree that what will come first is what? What comes before subtraction? Multiplication. So we'll multiply these things together first, and then we'll add and subtract. So we got 50 minus 30. And the 30 multiplies by 5. What's 30 times 5? 150. So you get negative 100. This one I made sure to include a negative number that you were supposed to plug in. Michael?
Are we allowed to do that on tests? Because you like skipped a couple steps in there.
Skipped what steps?
Well, instead of like bringing just like the 30 down and then timing by 5,
Oh.
you just skip straight to that. So that wouldn't be showing like all of your work. Are you fine if we do that on tests and stuff?
Yeah, that would be all right. The thing about showing your work, it's mostly for your benefit, okay? If you come down and you get 50 minus 200, I don't know what you did, where you went wrong. If you include as many steps as possible, I can find exactly where you did wrong and point that out and say, well, look how far you got, how much you did understand. So I'll give it's mostly about giving you partial credit, okay? So in that example, or in any example, if you get it right, and it's evident that you're not just using your calculator, sure, that's fine. But it's mostly if you get it wrong, or if I'm asking you to not use your calculator, and you would need to show more work than no work. So it's about partial credit, it's about proving that you know what you're doing. Okay, so we're going to put negative 1 in there, and the thing about replacing x with a number is that it means x needs to be exactly replaced by that number. So what I like to do sometimes, when the thing I'm using is negative, or the thing I'm using is actually, like, x could be equal to anything. X could be equal to y minus 5. Right? As odd as that seems. It could be equal to that. But to make sure that the correction, or the correct substitution is made, I like to put a parentheses where the x was and where the number is supposed to go. We put a negative 1 there, raise it to the 4th, minus 4 times negative 1 to the 3rd. So now we see negative 1 to the 4th means negative 1 times itself 4 times, although that's kind of a weird way to say it. I'm going to talk about that for a second. If I say that, say 3, let's go with 4 squared. A lot of people say this means 4 times itself. 4 times itself twice, which is 2 different things, and that sounds kind of weird. But let's just write that, okay, 4 times itself. That's what 4 times itself looks like, right?
Yep.
4 times itself, 4. Okay, how about 4 times, or 4 to the 3rd? Well, how do we say that?
4 times itself times itself.
4 times itself times itself, very specific and not ambiguous. Okay, but 4 times itself, 3 times?
No.
How many times is 4 being multiplied by itself here?
Two
One time.
Once.
It's being multiplied by itself once, not twice.
That's what I said.
Okay? 4 multiplied by itself once, twice, but that's 4 to the third. I only counted 2 times that we multiplied it
Four
once.
times 4 times 4.
It is 4 times 4 times 4.
Yep.
Right? We know what it means, but we say it in a funny way. So the way that I say it is 3 factors of 4. So that's how many factors you're going to use of that number. If you say times itself so many times, that always bothered me in school. I think it probably bothered at least a couple of you. So let's assume that that's true, and I'm going to start saying 3 factors of 4. It's more specific. And it's shorter than saying 4 times 4 times 4. Especially if it's 4 to the 7th, that takes a long time to say. Okay, 7 factors of 4. Alright, back to what I was saying before. So if we multiply -1 times itself 4 times, okay, so I'm holding up 4 fingers here, there's a -1 in each of them. -1 times -1 is 1, and -1, these other -1s times each other, -1 times -1, 1, so we have +1 times +1. So those negatives, if we're multiplying a bunch of negatives together, they pair up, and when they multiply together, they make positives, right? So if we have enough pairs to go around, we wind up getting a positive number, 2 times +1, and it's 4 times. Now we have only 3, so these 2 pair up, they make a positive, but then you multiply by a negative, and what we have is a -1. So we have 2, -4 times -1 is 4, so we get 6. Any questions on that? Hmm?
Nope.
Nope. Simplify the expression. What's another way we could say simplify the expression? We could reword it. Combine like terms. What makes 2 terms alike so that we can combine them? This comes down to just 2 things. Do you see any like terms up here? Which like terms do we see? Well, what did you say, Misty? Same exponents, yes. Okay. And this next part might seem a little too obvious. What? The variable has to be the same. If they have the same exponent but they're not the same letter, that doesn't make sense. So the same variable and the same exponent, that makes things like terms. So we can put them together. We cannot put a p squared with a p to the third or a p squared with a p to the first. It has to be the same variable, same exponent. So 4p squared, -9p squared, -5p squared together. We got -12p. What can we do here? Distribute. What do we get? 12p plus 21. Don't forget, even veteran distributors will forget to take the 3 and give it to the 7 from time to time. Just remember, 3 times 7, also we get 21 there. We have -5p squared, -12p, plus 12p. What's that give us?
Like
0.
terms.
What?
Aren't those like terms?
They are like terms.
Mhm.
We can put them together. They cancel each other out. We get 0 of them. Plus 21. And that's it. Simplified as can be. Same deal here. We just have an x and a y. So 4 cubed plus 5 times what's y. Y is -3. Making sure to parentheses around that -3, so we have multiplication. 4 to the third, what's 4 to the third?
4 times 4 times 4.
It is 4 times 4 times 4. And that's 16 times 4, and that's 64. Minus 15, and that's 49. Okay, any questions from the quiz? At any point? Yes, Carl?
So on the first one.
This
it was
one?
-10 to the 4, and
Yeah.
it ended up being negative.
Yeah.
But then on 23, when you did -1 to
Yeah.
4, it ended up being positive, so.
Okay.
How that worked.
How that worked is that what's getting raised to the 4th power right here? What's getting raised to the 4th?
-1.
Well, x right now,
Yeah.
right, in this expression. X is getting raised to the 4th. Whatever x is, we're going to raise it to the 4th. So that means that whatever x is, we're going to take that, exactly what that is, and multiply it by itself 4 times, right? So we come over here and we see that we have -1 raised to the 4th. Now, big difference, at least in the way that we write it down, is that there's parentheses around the -1. You see, we include the negative in the parentheses and then apply the 4th power to the whole thing.
Okay.
So then that means -1 times -1 times -1 times -1.
Yeah.
Whereas this, if we wanted to come out positive, we'd have to do -10 times -10 times -10 times -10. But the understanding that we all agree to is that if I want that, if I want -10 times itself 4 times, or 4 factors of -10, is that I'll put parentheses around the -10, then we'll multiply it all together. But as it's written, we'll be assuming that the person who wrote this down meant that only 10, the number positive 10 is raised to the 4th, and then the negative, that's really multiplied by -1, right? That's what negative kind of means. So that multiplication by a negative comes after the exponent. Just a little thing, in particular when you're writing down your work and you're trying to convey to me that you know what you're doing. If you write down -10 to the 4th and you end up getting positive 10,000, that'll be a little confusing. I'm gonna have to go back through your work and see exactly why you did that. Was it correct? Were you supposed to take -10 and put 4 factors of it together, multiply it together, or did you just do this as it's written? Did you just do it incorrectly? Any other questions about the quiz? Any questions about another homework problem that you had trouble with? Yeah? No? Yes?
Yeah, can you go through like 41, 42, or 47? Just conversion things.
That's a good book.
On 1.1.
Okay, thank you.
Mr. Stewart?
Yeah.
Can I go back?
How do you ask?
What? Oh, okay.
Thank you. All right.
No.
41, 42, or 47.
I get in bed at like 9:30, but then I'm
All right, let's do 42
Yeah, exactly.
and 47. Might as well. Won't take too long. 42, just to introduce the idea in case we're unfamiliar. 6 feet per second. I like to write it this way. It's very clear where everything is. 6 feet up here, 1 second down here. And when I convert to different units, it makes it so much nicer to work with. So what do we want to convert to? Miles per hour. Okay. Well, we need to convert the feet into miles and the seconds into hours. Okay. So let's just go with the feet first, because why not? So how do we convert from one thing to another? How would I convert, say, feet into inches? How would I convert inches into feet? Divided by 12. Because there's this equivalence of 12 inches to every foot, just like the relationship they have. Okay. So what's the conversion between feet and miles?
How many feet are in a mile?
That's what I'm asking. What's that? 5 what? 5,280. So you remember the Titans? You'll never forget. Okay? So there's 5,280 feet per mile. We want in the numerator to wind up with miles. Okay? So miles 1 mile is equivalent to 5,280 feet. Okay, this is not a mystery, it's not a magic trick, right? What do we say about 1 mile and 5,280? What's the relationship with each other?
There's 1,280.
5,280 feet in a mile, so they are equivalent, right? They're the same thing. So if I were to actually divide this out and come up with like one number, what number would I get? Something divided by something completely equal to that thing. 1, right? A thing divided by itself, something equivalent would give you 1. So we're multiplying by what? We're multiplying this thing by 1. Can you multiply by 1? It doesn't change anything. It doesn't change how much it is. It just changes maybe how you see it, what units it's in, what it looks like. Okay. So we divide by 5,280 there. Right? That makes sense. We take the number of feet. Let's say we had 30,000 feet. We don't know how many miles that is. Divide it into chunks of 5,280. And however many of those you have, that's how many miles you have. So you take the feet divided by the number of feet in a mile, and then you'll have how many miles it is, which is not very many miles, right? But we're also, this is 6 feet per second, it's not 6 feet per hour. So that the number that we actually, it's going to be a little bigger than that. So we converted the feet into miles, right? Because the feet cancel with the feet. Cancels those units. So next, we're going to multiply by something that converts seconds to hours, or maybe we'll convert seconds to minutes, and then minutes to hours.
60?
60 what? Seconds in a minute, right? So we know we want to cancel seconds in the denominator, so we're going to put seconds up here in the numerator so that they cancel. There's 60 of them in 1 minute. Okay, but we need hours, so what else do we need to do? Multiply that by 60. 60 minutes in an hour. Minute units cancel. And now we see all of our units have canceled. All we're left with is miles and hours. And once we do all the math, we come out with how many miles per hour that is. Okay? Could I multiply 6 times 60? Can I do that with a piece of paper and a pencil only? Is it possible for me to do?
Yeah.
Yes, I hope so. Can I divide that by 5,280 with a piece of paper
Yeah.
and a pencil? Okay, I hope so. Long division. Might take a minute to kind of rejuvenate our minds and remember exactly. Okay, so it's possible. So if it's possible, I can do it, then I'll go ahead and use my calculator to do it faster. But if I'm using it because I don't know how to do it, that's enough to use my calculator. So 6 times 60, 360. Divide that by 5,280. 6 times 60 again, so we're going to multiply this by 60. There's 2 60s. So 4.091. Let's say 4.09. 4.09 miles per hour. You might notice I may have seemed to have violated one of my rules that I told you, or maybe you just completely forgot what I said, which is fine. I said if you start with fractions, end with fractions, unless it's an actual thing. This is actually miles per hour. If it was just multiply these fractions together, I would expect it to stay as a fraction. But if we're just trying to convey some information that would be useful in everyday life, let's just report it to a couple of decimal places and call it good, because now we know, we get an idea. That's pretty slow. 4.09 miles per hour. Very, very slow. That's like walking. Not very fast. Okay. 47. Do a couple different things. So a rocket sled on a track in an Air Force base in New Mexico. A rocket sled travels 3 miles in 6 seconds. That's much faster than this. Write the average speed in miles per hour. So, first, we need some kind of a speed. Do we know how fast it was going?
3 miles.
3 miles in 6 seconds. 3 miles in 6 seconds. Okay. Which is like half a mile a second. It's really fast. Well, that works. We don't always have to say miles per second, 1 second. We could say 3 miles per 6 seconds, especially if we're just going to convert it to something else in just a second. Yeah.
Can we write it like just like continue that line out and then just put like a like horizontal line?
A horizontal?
Yeah.
Sorry, like this? Just keep going?
Yeah, and then when you're multiplying, just put horizontal lines.
Oh.
Like space them out.
Vertical then. Vertical lines?
Yeah, that.
You could. I don't know that I would use those lines because, you know, what do those lines mean? They don't have like a mathematical meaning, and so it might be confusing. Think if you passed your notes to somebody else, would they be confused about what you wrote down? Maybe, but something like that. But if we just do write one long horizontal line, and then just maybe put multiply, and a little dot in the center for multiply, we could do that. Because that's all we're going to do here, right? We're going to multiply straight across. So yeah, that would be the same thing. Well, we're going to need to multiply by an equivalence ratio, just like we did here, okay, to get it into miles per hour. Well, it's already in miles, right? So that's done. We just need to convert the seconds into hours. How are we going to do that? Yeah.
60 seconds on top, and then
Okay.
like 1 minute on bottom.
1 minute on bottom, very good. Okay, now we have canceled the seconds. We're at miles per minute. So we'll multiply by 60 minutes. Cancel out the minutes. 60 minutes per hour. And now we're in miles per hour. So we just do 3 times 60 times 60. And divide by 6. Or we could even just do cancel that 6 with that 6. That's a 10. 3 times 10, 30 times 60. 1,800
Yeah.
miles per hour. That's fast. Scary fast. So when I see really fast speeds, I like to think, how long would it take this thing to get across the U.S.? How wide is the U.S. about? Guesses?
5,000.
Huh?
5,000?
5,000? Okay, guessing. Good guess. Less? Nobody know?
3,870.
Wow. I wouldn't be surprised if that was exactly it. It's about 3,000. Okay, from west to east coast. Now, if we go from California up to Maine, you know, that's going to be a farther trip. It's going to be more miles. But it's about 3,000 across. So how long would it take this guy to get across the U.S. real rough? About 2 hours, more or less. Which one is it, more or less? Less than 2 hours. More than 1, less than 2. Ooh, that's fast. How long does it take you to drive across the country? A lot longer. Few days. It took me 2 days to drive from San Diego up to here. But, you know, you could probably do that in 20 hours if you drove straight through. 20 hours for me to drive in my car from there up to here, from San Diego to here. That is only 1,200 miles. So, real fast. That's what I'm saying. 1,800 miles an hour. It's a fast speed, in case you didn't catch that. Any other questions? Questions? Okay, let's pass in our homework, please. If you don't have your homework, what am I getting from you?
Pink slip.
A pink slip. Maybe we don't have any pink slips. Maybe I will just weep with joy when I'm by myself.
Ricky has your face.
What?
Well,
You can leave those,
okay.
it's fine.
I got peeling back in it
Bothers me
like
more
5 hours
how much time it
later.
takes to get them off.
I couldn't eat my dinner. Look at turkeys come out of my leg upper lip.
Remember
Oh, by your steak.
that if, when you walk in here, you don't have your papers stapled, you need to do that before the late bell rings. It's not hard. If it's it's ideal you're in your previous class, you know your work together. For this class, and a notebook, a piece of paper, maybe a calculator's ready to go, and you have your homework in hand, you save it, you sit down. No big deal. All right, so 1.1. What's 1.2 about? Oh, we did that, and we're on 1.3. Okay, we're gonna solve linear equations. That's gonna start out pretty simple, and it probably will at some point challenge each of you. If your day is done and you didn't have any challenges solving these equations, that's nice. And you know, it's nice to solve equations and to get the right answer and all that kind of stuff. But it's a little boring for a teacher, somebody who's have all the answers. Rejoice with you, but also I'm interested in people who are having trouble. So I want to see if that's happening. So I will periodically give you a problem to work on individually. I'm going to see how you do individually, and I'll come around and assess where you're at. If you need some help, I'll help you. If lots of people have the same problem, I'll address it up on the board. And always raise your hand and ask questions if you want. Okay. So let's get started. But before we start, I want to start us off with a good analogy for equations. So, what is this thing? It's called scale. Somebody in another class called it an old-timey scale. It is kind of an old-timey scale. Because we have scales now that you stand on. There's springs and stuff, and it just tells you the number. Okay. You might find this amusing, you might not, but I always like to think there was a time when those scales didn't exist, where you didn't just stand on something and it told you how much it weighed. And so the same way I am with calculators, in that it's nice, they're cool, but don't let them take over the understanding. I wonder if maybe when those scales came out, the guys who are using these old-timey scales were like, oh, these young kids and their scales with the numbers. That's just, is that funny? So, it's just something I thought of. So how do these scales work? Yes?
You put an object on one side, you
Yep.
don't find the weight of, and you put like measured weights on the other side.
Yep.
and balance it out.
Good. Have you guys used, they're not exactly like this usually in like a chemistry class. You guys use scales in chemistry class? Like you slide the weights over? Same kind of a deal, right? There's a thing over here, the weights, you slide them over, and their closeness to the bulk represents, you know, a certain amount of weight. So, yeah, you set something here, and you set something there, and what are you trying to get it to do?
Balance.
To balance. We know it's balanced because it's flat, right? And usually there's a little thing that points straight down, tells us, you know, it's balanced. Okay? So how would this maybe relate to what we're doing today? Equations. They're just like scales, right? We could put an equal sign right here, equals in the middle. Put some variables and stuff over here with some coefficients and whatnot, maybe some constants. Put some other stuff over here, and when we put an equal sign in there, it means this. It means they are balanced. Okay? And what's our goal as we solve the equation? We're looking at this balance. As we manipulate the equation, what's our goal? Make both sides equal to each other, or they're already equal to each other, so for them to remain equal to keep the equation balanced, okay? So, if you're somebody who thinks do the same thing to both sides because that's just what I was always told and I remember that, you're not alone. I've met many people like that. But the essence of it is very simple. We're adding the same thing to both sides, we're subtracting the same thing to both sides, we're dividing both sides by the same thing, because we don't want to violate the balance that we had to start with. Okay? So Now this might seem condescending or pedantic or something, but I hope it doesn't, because it's a nice little visualization. Okay. If we have an equation like 3x equals x plus 2, okay, first we have to represent that equation. Well, there's an x, there's another x, there's another x. There's an x that goes over here, and there's a unit, so there's 1 and 2. Okay? Well, we're trying to figure out what a single x is worth, right? So, well, for one thing, we have x's on this side and x's on this side. Usually when you use scales, you want x's, you want your unknown stuff over here, and you want your weighed out weights over here. You know, or vice versa. But you want your unknowns on one side and your knowns on the other side. Okay? So how are we going to get, what operation would represent taking this weight off of this side? Subtraction of x. Okay? So physically we would take these x's off of the thing, right? I don't know if I can, I don't think I, oh. Take that x off. I also have to take this x off. Yeah? That's why we subtract the same thing on both sides, not because we were told to, but because it's a balanced system, and if we were to not do the same thing to both sides, it would become unbalanced. Okay? Well, can we see what x is already?
Yeah.
Yeah, certainly. They match up. They correlate perfectly. 1x for 1 unit, right? But, you know, that's not good enough. So can I subtract x from this side?
Yeah.
I certainly could, but then what would I have to subtract from this side?
1.
Well, let's say we don't. Let's assume we don't know what that x is 1. So what can we do that's the same thing to both sides? That gets, it also gets just 1x on this side.
Add a unit.
If we add a unit to both sides, if we add a unit here and a unit there. See, now we've got knowns with our unknowns. We like unknowns to be, you know, by themselves. So we'll just take these off. Certainly could add one to both sides. There's no reason why we can't do it, but then it gets our x's with.
You could add that's no.
We just took x's away, right?
Subtracting x.
Okay, but see, the thing is, if we have to do identical things, if we subtract an x from this side, what we have to do is subtract an x from this side, but let's assume we don't know that x is 1. And Michael?
Can you divide by 2x?
There we go.
Or
Well,
just
divide by
by
2x?
2?
How about just divide by
2.
2? Take half, right? We have 2 of these. We only want half as much as that, right? So we'll take half of this and half of this. If that's equal to that, then half of that should be equal to half of that. So we'll take, so it looks the same, it looks like subtraction, but I'm really taking, I'm looking at half of that side versus half of this side, and now x is 1. Okay? So that's what our system is. That's why we do the same thing to both sides. Okay? Now, let's look at this in a different way. X plus 2. Okay. Well, what did we do? What was the first thing we did before to get subtract x? Okay. Well, in terms of weight, this is positive weight, right? And what would be negative weight? How, if positive weight pushes down,
Negative weight.
negative weight, how could you pull up on that scale? Take a look at the pictures you see. A balloon, right? A balloon filled with helium, that could represent negative weight. So we can subtract an x from this side, and subtract an x from this side. Those are balanced. The x's didn't go anywhere, but certainly this x, excuse me, this x with this x cancel. Okay. So now we have essentially 2 x's, and over here this x and this negative x and this x cancel, and we have just 2 over there. So what do we want to do to both sides? Got two x's over here. Got 2 units over here because this x and that negative x are canceling, so we essentially just have 2 here and 2 x's here. Divide by 2, and to represent that, not sure what we do. Oh, it doesn't match the equation, so it won't do it. Let's do that. But if we divide everything by 2, which now these have canceled each other out, let's say. We can get rid of them because they're canceling each other out. And now we divide both sides by 2, take half of this, x is 1. So let's start something simple. That was all just to display to you why we do what we do when we mess with equations, because it's a balanced system. So let's start off slow and do number 13. I'm going to have you do this individually in your notes, so go ahead and get started whenever you're ready to. So what's the first thing we're going to do? Subtract 5 from both sides. And what's 3 minus 5? Negative 2. The thing we have to be careful about, I have seen 3 and 5 and then 8. Okay. Now the numbers 3 and 5 can combine to make 8, but what's the mistake there? We have a negative 5. So we're not adding 3 and 5. We're not even adding negative 3 and negative 5. We're doing 3 minus 5. So make sure that you remember that. To represent 3, we can look at this number line. 0. Here's 3. And then minus 5 would be to go back. 3, 4, 5. So negative 1. Don't get mixed up on that. Okay? Next we have to finish. Next, we have 2 p's on this side. We have negative 2 units on this side. So what are we going to do? Divide by 2. Half of that side versus half of that side. Well, this is great. Half of this side is just p. That's what we want to know. Half of this side is negative 1. Negative 1. All right, so let's throw some other challenge out there. Change the color. Number 30. 6 minus 5 cubed equals q plus 9. So again, this is you, it's all you. See what you do, see how it goes. We are in 1.3 in case you're trying to find it out.
1.3.
If you want to have it up there. You don't really need to, because I already put them up there.
I didn't give it. I asked you if what it was. 30.
Oh, yeah, you're doing it.
How'd you get that? I asked you what you got, and it said write it down. I was like, did you get it? No, I was like, did you get negative 25? Negative 25? Negative what? Nine.
Put it down the bottom.
I was like, how? You're just gonna write it down like that?
Okay, looks good. How's this different from the previous problem?
Q on the other side.
Got Q's on both sides. Got variables on both sides. Alright. So we had that similar situation. Here we had variables on both sides, and we said that how a scales works is we want our unknowns on one side and our knowns on the other side. So we don't want to have knowns on both sides. Okay? And try not to think of it as moving something from one side to the other, right? If we subtract a Q, it's like we're taking something, taking it away. We're not moving it over here, we're throwing it away. We're getting rid of it. Okay? So that moving idea can cause problems later. So we want to remove like this Q, right? Right? This Q. What does negative 5Q mean? Negative 5Q. Like in that, on the scales, what would that look like? 5 balloons, right? Pulling up like that. So that's kind of a weird idea that you have negative 5 of the thing that you want to figure out what it is. But so sometimes conceptually it can be weird if we try to imagine what it actually means. It can be odd. But we can do that with numbers. We can make them just negative and multiply them by negatives to cancel out the negative and so on. So we'll remove that Q. We'll just take that Q away, and we'll also take a Q away from this side, which would look like adding another balloon to the other side. 6 minus 6Q equals 9. Okay, that's good. We've got 6 units over here, also 6 balloons, a Q on them. We're not sure how much they are worth. And on the other side we have 9 units. Well, again, we want unknowns alone on one side and knowns on the other side. So here we have unknowns, and we don't want the knowns on that side with it. So what do we do? Subtract 6 from both sides. So the 6 minus the 6 is 0, so that's nice. That just leaves negative 6Q. 9 minus 6 is 3. Divide by 6. Q equals negative 1/2. Somebody asked a good question. If it's negative 1/2, do we write it negative 1/2? Or do we write it negative 1/2? Or do we write it negative 1 over negative 2? Which way should we write it?
Doesn't matter.
Doesn't. Okay. All of these are equal. Negative 1 divided by 2, a negative divided by a positive, is a negative number. Right? So that conveys that truth. That is going to be a negative 1/2. This negative out front says the number 1/2 is negative. Okay. This is the same thing. 1 divided by negative 2 will also give you a negative number, negative 1/2. This is not typical. Not typical. Either one of these is what you'll typically see. So the negative out in front of the 1 or negative in front of the whole fraction. Yeah.
It's alright if we wrote it in decimal, right? -0.5.
No.
No, okay.
Okay. So, and I know it seems like I'm being like a dork or something, or just mean. Okay. But here's the thing. It's true. That negative 1/2 is the same as negative 0.5. Okay, that's fine. So if you did write negative 0.5, I'm not going to mark you off or something, because they are equal. But I try to break you up this habit, because if, again, for example, we have 1/3, and you tell me 0.33 or 0.333 or any amount of 3's will be wrong. They won't be equal. Okay? I do want the actual exact answer. Okay? Unless we're doing a problem that involves money or miles, or hours, or something that actually has a unit that decimals makes more sense in the context. So at the end of the problem, if what we're solving for is the number of miles that we traveled, negative 1/2 miles, which is possible, we can go backwards, okay? Then, sure, negative 0.5 miles, that makes more sense in the context. Okay. But particularly with answering problems with 0.3 instead of 1/3, and even worse, using 0.333 whatever to multiply by 5/6 or something. Then turning 5/6 into a decimal and turning 1/3 into a decimal, multiplying them together, they're both not accurate. And then you're going to multiply them together, and it's going to be doubly not accurate. It's going to perpetuate the error. It's not going to be exact. Okay. So keep it as fractions, especially for computing. And at the end, unless you're saying, negative 0.5 miles, hours, gallons, whatever, just leave that as a fraction. Okay. Just a rule of thumb. All right. So variables on both sides. What do we do? What do we do when we have variables on both sides? Well, again, not move them. We're not moving them from one side to the other, but we are getting rid of them on this side and getting rid of an equivalent amount on this side so that only one side contains unknowns. Yeah? Okay. So now I'm going to have you do this problem, but just write it down. Don't be working on anything. I just want to share something with you that's both true and funny. I enjoy it. So you can write this down, then I'm going to talk at you. And the more I tangent, the more, I guess, the less homework we have. Okay, so look at it in that sense. So maybe this problem is a challenge for you. You don't know what to do. Don't just sit around and wait for me to tell you how to do it. It's not about, I don't know how to do it, you tell me how to do it, and now I know how to do it. Okay? What you need to know is that this is an equation, both sides are equal. I can do whatever I want to both sides, as long as I do the same thing to both sides, because it maintains that equality. And just try anything, okay? And actually try something. If you just sit around and wait for me to show you, it's like it's a part of this instant gratification society that's, it's not like it's your generation's fault. My generation had it too, generations before us, and way back we wanted to get as satisfied as quickly as possible, just to be gratified as soon as we possibly could. Okay, but there's something in the struggle and the seeking out and the finding and the creating even of knowledge. Okay, some knowledge you have to find out. There's just things that are true. There's facts about people and things that are true and you can't change them. But there's knowledge that you can create, like how to solve a problem like this. Using approaches that I've used before, I can apply them to a new situation, and I can actually create like this set of steps that are mine, that I understand, and that get me in. So just to talk about the seeking out and the creation of knowledge, and the obtaining of knowledge, I want to share a video with you. Oh, wait. It's over here. It's in there. There.
So I have an iTelephone. I do. Which means I have Google on my phone. I'm guessing a lot of you do. I have Google on my phone now. It's ruining our lives. I don't know if you've noticed, it's ruining life. Because we know everything. But we're not a lick smarter for it. We just know. You don't know something? Wait 2 seconds. You will know. Having Google on your phone is like having a drunk know-it-all in your pocket. There's no time for mystery or wonder. You're just like, how do they make glass? And you know. But the time between not knowing and knowing is so brief that knowing feels exactly like not knowing. So life is meaningless. I've literally been in bed in the morning, alone, just like, where's Tom Petty from? But I feel nothing, because there was no time to not know. Listen to me. There was a time, and I don't mean to get all Andy Rooney on ya, but there was a time that if you didn't know where Tom Petty was from, you just didn't know. And you felt that yearning and that deficit in your being. And you'd go around and ask actual people, like, where's Tom Petty from? I don't know. I don't know. I don't know. And now I'm impregnated with wonder. And then they go and ask people. Until one fateful day, you see a girl wearing a Heartbreakers t-shirt, you rush up to her and you're like, hey, where's Tom Petty from? And she tells you, Florida. And a wave of endorphins and pleasure and meaning would wash over you. And you felt something. And that's how you met your wife. Do you understand? Your wedding song was Refugee. Did Biz laugh? Thank you very much, everybody. Good night. Thank you.
Okay. So, this guy Pete Holmes, pretty funny guy. And what'd you think?
I think it's true.
Huh?
I think he's got a point.
I think he has a point. Okay. Something we said for Google. It's really cool. You can look things up, and now we can know things. But it's kind of true. Like, there's this lack of wondering what the answer is for a while. What is it? And then the satisfaction that comes after finally finding somebody who knows and they can tell you, or finally the satisfaction with a problem like this of trying it over and over and over, and then figuring it out the best, okay? The best feeling, okay? Not that it's superior to something else, but if you can't figure it out, then you tried everything you could, you know you gave it your best effort, and then you ask somebody who knows, and they explain it to you, and you're like, oh, I was so close. I had done a lot of work in the right direction. That feels really good too. And then to know is very satisfying. But to wait around until somebody just, picks up your hand and makes you write it out and shows you exactly how to do it, not as satisfying. Okay? You might know it, but it won't be as satisfying, and it won't be as long-lasting as if you force yourself to create that knowledge, or at least get as close as you possibly can. So the first thing I would say is in any problem, try anything, as long as, in this context, it's mathematically allowed. Okay? Try anything. Some things won't make sense. It'll turn out to create extra steps. That's okay. And we can trim up a clunky process, but it's better to have some kind of process than nothing, just to start from scratch and we show you and you try to memorize that. Okay? So try something, try anything. And just keep on trying. If only after you completely run out of ideas. Oh, this is the other thing. Don't think that because you can't envision the entire process from the beginning that you shouldn't proceed. If you can't see the end before you begin, that's okay. That's how most problems in life are. You just try something, and it doesn't work, or it does work. It gets you close. Okay? Write down the next step. I literally had somebody in here the other day who said, I don't know how to do this problem, on that practice test we took. And I said, well, what could you do? And they said, well, I could distribute. Okay? So I said, distribute. And as soon as they wrote down the results of distribution, they said, oh, that's what I would do. Just seeing what you yourself have written down can oftentimes inspire you and open the door to what the next step could be. So, we'll run through this together and the last problem together as well, just for the sake of time. So we could, as I just said a minute ago, we could distribute, right? We can try that. Give it a try. Maybe you don't know what's going to happen when you distribute, what it's going to look like, but you try it and you see what the next step looks like. So we get 7t minus 21. Remember to get that 7 over to the negative 3. And we get 2t minus 18 plus 2t. Okay. Well, what can we do now? We got like terms. That's one thing that we could do. Okay? Could you do some of these things all at once. Can somebody do this in fewer steps? Sure. But if you make some progress on every step, that's the ultimate. That is all that matters. Okay, so we'll look at that. Now we have an equation with variables on both sides, just like before. Now we've boiled it down to something we feel comfortable with, right? And so now we can approach it the same way as we always have. So after distribution and collecting like terms, look at that. It looks just like a problem where there's variables on both sides. Okay? So what are we going to do? What would you do?
Add 21.
What's that?
Add 21.
Add 21. Great. Okay, so that is so that's 3. Fantastic. Subtract 4t. Great. 3t equals 3. Divide by 3. T is 1. Now, like, I wouldn't have added 21 at that point. Right? That's a different order than what I would have done. And I only bring it up because sometimes I'll do stuff. I'll do an equation, I'll solve an equation, gets all done. Somebody else says, well, see, right there you added 21, but I subtracted 4t there. Like, yeah, it's the same thing. We eventually both will have added 21 or maybe added 18 to both sides and you get a negative and I get a positive. But it's all the same thing. If you come out with the same answer and you follow steps that were mathematically legal and you did them all correctly, we got the same answer, with a slightly different root. Okay, it's all the same. What I think will be, yes, the last one. Let's do 44. We went a little bit long in a couple of things, so I would just put this to you and see what you do. We'll come up with something together right now. Let me say it this way. If this was a 5D plus a 2D, completely different problem, what would you do with these two before? Let's combine like terms, right? They're like terms. Are these like terms? Yeah, these are like terms. What's the difference? You got, well, we have fractions, and therefore we need to find a common denominator. Very good. Okay, what's that common denominator going to be? It's going to be 40. Okay, so this is going to be what over 40? 8 over 40, and this will be 5 over 40 d equals 2. Right. And they're like terms. If we were to put these together, we would just do 5 plus 2 is 7 times d. Same thing here. 8 40ths plus 5 40ths is 13 40ths. D equals 2. Okay. We want to know what d is. We know that if we multiply d by 13, and then take that and divide that by 40, we would get 2. So how do we reverse that? Reverse that. Multiply by 13, divide by 40. Multiply by the reciprocal, multiply by 40, and divide by 13. It's the exact inverse of multiplying by 13 40ths. So we can write that 2 over 1 if we like. This cancels out. We're left with 1d equals. There's no simplifying that we can do. We can't cancel common factors here, here, or here. So we've got 80 over 13. So if you want to do yourself a favor, don't view your homework as something to get done, to finish, to finally be able to push to the side and bring to class done so you can get credit. But the people who wrote the book, don't pack up your stuff quite yet. You got plenty of time. You don't need 5 minutes straight of packing to get everything in the backpack. I'll give you enough time. Make sure you get out of the door and get some lunch. The people who wrote the book and wrote the homework wrote it in such a way that you're trying to build on top of previous skills. If you notice, I just took homework problems, one from each kind, right? They're broken into different types. Right? First one, variables on one side. Next one, variables on two sides. Next is almost variables on both sides. You just do some distributing first. After that, We have just combining like terms really, but fractions are thrown in there, saving fractions for last, right? Because they can be intimidating. They're just building one thing on top of each other, of the other. So if you on your own can see, once I distribute, then I just have variables on both sides. That's the kind of problem I've already done. Great. I found a way to reduce this problem to another problem. And that's what a lot of complicated math is, trying to reduce a complicated problem to a simpler problem. But that's all I have. You can keep working for a few minutes and pack it when you like, or you can choose to pack it now. But whatever we do, we're going to be sitting in our desks, not standing at the door. Because I hate it so much.
What do you get for